Okay, today's last talk. A class of beyond standard model. Let's welcome Dr. Ye. Please.
Thank you for coming here, and thank you for staying here with me because I'm the last speaker today. So I was told that some of you may be picked up by a bus at 6:15, so this means I probably have to finish the talk within 15 minutes. Okay. So I probably will cut some details. Okay, so this is the title that I'm going to talk about. So today I will talk about causal models targeting these DSM scenarios. So let me first give you a brief introduction. So what is something SUSY? We know that supersymmetry is just a space-time symmetry that relates fermions and bosons. So it has very good motivations from theoretical and phenomenological points of view. So theoretically, SUSY is required in some fundamental theories, such as semi-realistic string theory, because SUSY can introduce the fermions to an otherwise bosonic theory. In addition, the SUSY can be used to cancel some tachyonic states, such that the system is ensured to be stable. Phenomenologically, people like to study SUSY at no intermediate scale because you can use it to solve the hierarchy problems and preserve the naturalness of the theory. However, experimentally, a large portion of the supersymmetry parameter space, model space, have been ruled out for the low-scale SUSY. So people like to consider supersymmetry at least about the TeV scale. On the other hand, in the low or intermediate SUSY models, people usually are working within the perturbative regime. This is because the strong dynamics is very difficult to calculate, say, some non-perturbative effects associated with the strong dynamics. But these strongly coupled sectors actually are quite generic, especially in some fundamental theories. And the study of the strongly coupled gauge theory has shed light on the non-boundary calculations. So normally people may consider to describe a strongly coupled sector by a weakly coupled sector in the bulk, following the gauge gravity rule. So one example in supersymmetry scenario is something called the holographic gauge mediation. That is, the strongly coupled gauge sector can talk to the weakly coupled visible sector near the massive fields, which are charged simultaneously under both sectors. Okay. So in this talk, I will introduce a type of models which may be realized as a field theory realization of such scenario. Another motivation actually comes from dark matter. We know that dark matter constitutes a sufficiently large portion of the universe and is one of the strongest evidence of the BSM physics. However, its nature remains, a lot of its nature remains unknown. So practically, people like to invade the dark matter in a hidden sector, which has like the gauge fields and the matter fields. And so furthermore, if this hidden sector has strong dynamics, then what will happen? The matter fields charged under this hidden sector may form bound states, and these bound states may escape the experimental bound in some sense. So here, that is the features that we hope that our models can satisfy. So it has a strong hidden sector with strong dynamics, kinds of alleviate naturalist problem in the standard model. And the supersymmetric question will have significant difference feature than the usual low-scale SUSY because you have the bound states. And we also hope that our theory is possible for gut underlying theory. And this model will also provide various bound states. Some of them may be the dark matter candidate. Okay. So here is the setup. So we extend the stat model by adding a SU1 gauge group and some mu scalar particle fields. So we hope that this SU1 gauge group is in the confinement phase with a confinement scale at 1 TeV. And all the standard model particles are usual on the hidden gauge group, but the new scalar particles are charged on both the standard model and the hidden gauge group. At this stage, this model is not supersymmetric because all the new particles are just scalar. And we refer to these scalars as messenger scalar. So here is spectrum. This is a table of the charges of the new particles. So here we use capital letter to denote this new scalars. So they have the standard model fermion-like charge, but then they are charged as fundamental under the hidden SU gauge group. So we can see that their principal charges and reminds us that some of them may be embedded into a 5-plate or 10-plate under SU5 gauge group, which is a potentially unified group of the standard model gauge group. But here, let me remind you that at this stage, we haven't fixed the number of generations of each flavor. So this doesn't mean that we have the whole spectrum. So some of them may be absent. And the number of generations of each type of field will be determined later. Basically, this will be determined by the 3 constraints. One is the non-double constraint. The second is from the gauge coupling implication requirement. And the third one will come from the requirement that the hidden SUN group is really in the confining phase. And here we also have the Higgs sector, which includes 2 Higgs doublets. And we notice that the Higgs doublets are mutual on the hidden gauge groups. So our Higgses are still elementary particles. This is quite different than the Technicolor neutral Higgs or composite Higgs models.